based on counting the number of possible states that spin and orbital angular momentum allows for us at each one of these energy levels. And I was thinking, 2 states, 6 states, 10 states, 14. Where have I seen those numbers? 2, 6, 10, 14 states. They look familiar. Oh yeah! It's the periodic table. Because if I look at the periodic table, what I've got are these elements in these first 2 columns that are filling up their S states. And then the 6s, let's see, there's groups of 6 elements over here, the P block, where the states are filling up electrons into P states, and there's 6 total electrons that will fit into those. And then I've got these transition and intertransition regions. Now, traditionally, the way we look at this is the transition elements, these blocks of 10 elements across, those are elements that are filling the D states, 10 states each. And then finally, these intertransition, or rare earths, are 14 across. Now, when you look at periodic tables, they don't quite match up a lot of times. So I'm thinking what I have to do with this one, for example, is in terms of the S states, well, clearly down here, if I put 1 electron into a 1s state, that's going to represent hydrogen, but where is element number 2, helium? And they put it way over there. So, scissor time, right? So what we need to do is we need to cut off the helium block over here, at least in terms of which states are being filled, and bring it back over so it's next to hydrogen. So that's the first change we have to make. Now, of course, helium is over there because chemically it's non-reactive, similar to the elements in that column, but based purely on occupation of quantum states, helium belongs over here in the S column. So imagine the excitement back in the late 1920s, early 1930s. Once physicists had mapped out all the possible energy states, what they realized was the Schrodinger equation predicts the periodic table.